Good evening, guys. Welcome to the first Introduction to Astronomy talk for 2022. We're doing it online for obvious reasons. So welcome, thanks for joining us. Let's get started. So I thought, well, it is the first one for 2022. So an ideal topic would be to do just a fun quiz as a sort of a vehicle, if you will, for a revision of a selection of topics we covered last year. Some topics were quite popular, so I pulled some out. As you'll see the list there: dark matter, special relativity, the sun, the night sky, star clusters, and water on Mars. So the format is, it will be a multi-choice question. You can pick your answer, and yeah, don't be shy. It's pretty relaxed, so don't be shy. Put your answer in the discussion thing on the side of the screen there, and then I'll give you a few minutes, and then Steve will say, yep, so-and-so's, or we've got 5 people here who've got the right answer and so on. But that's no big deal. The whole point of it is then I lead on, and I've got a series of slides just sort of revising some of the key points from that particular talk. So it's nothing threatening. It's actually just a bit of fun, low-key fun. So if you've got any questions, just put them in there as well. And probably I'll try to answer them. Steve will just pipe up perhaps at the end of each topic. I'll make it clear that's the end of that topic. And then any questions related to that we can bring up. If any people watching this now or watching it in the future down the line, if you haven't got any handouts for any of these topics, they are here. I've got them on my computer. Don't be shy. Just send me an email. Even if you don't see this in a year's time, you stumble across this, think, oh, I'd like one of those handouts on the night sky or all of those. Thanks very much. Hey, send me an email, membership@astronomy.org.nz, and I'll go, hey, that's really cool, attached other handouts. So it's fun putting the handouts together, and it's all about, having fun and sharing information. So let's move along. So the first topic, dark matter. Now, this was actually the title slide. A lot of these slides are either taken or adapted from my original talks from last year. So here's one for you guys, just to throw in the mix here. Who can please name this object that was on the front slide and my title slide for the talk on dark matter, and just a couple of words, 2 or 3 words on its significance to dark matter. You don't need to get too serious about it. So Steve, we'll actually come to that shortly. So that's your first little bit of thing if you want to start doing that. Now, let's go on to the questions, the multi-choice. It's on about the evidence for dark matter. Which of these 5 important pieces of evidence was Vera Ruben responsible for? So I've listed 5 really important key pieces of evidence for dark matter. So A, high velocities of galaxies and galaxy clusters. Or was Vera Ruben responsible for rotational velocity curves of spiral galaxies? Was she responsible for discovering hot gases in galaxy clusters? Was she responsible for identifying the gravitational lensing around the bullet cluster? Or was she responsible for some important bit of evidence for dark matter that was hidden in the cosmic microwave background? So have a think about that for a minute, guys, just for a minute or two, and I'll flick over to the answer real soon. Okay, 1, 2, 3, over we go. And the answer was B. Vera Ruben was responsible for identifying or studying the rotational velocity curves of spiral galaxies, which I'll now talk about in some a little bit more detail. Anyone popped up, or they're all a bit shy there, Steve?
No, we got Joseph came in super quick with the correct answer, and Mitchell came in there just a little bit after. So Joseph and Mitchell, well done.
Hey guys, when when we get live talks and stuff, come along. So from this talk, I'll have some. I normally have chocolates and I throw out with it when we do this in live in person. So come along to the talk and when we next live one we do, hopefully in a month or 2 or 3 months when it happens, and I'll have some chocolates for you that I'll bring in related to this. So well done. Anyone any takers for the name of that object? No.
Well,
okay.
So far, no.
Okay, that's all good, guys, because I'll talk about it shortly, actually. Yeah. So briefly, the high velocities of galaxies and galaxy clusters, that was a Swiss-American astronomer by the name of Fritz Zwicky, quite an eccentric sort of character. And it was in the 1930s that he noticed that galaxies were zooming around within the galaxy clusters, and the velocities were just too high for them to be held together in a galaxy cluster. So that was him. We'll talk about these shortly. Hot gases and galaxy clusters, that was all picked up as the generation of galaxy, or rather of X-ray satellites, X-ray telescope satellites were launched above the atmosphere. Gravitational lensing in the bullet cluster. Yay, that was the object. That picture was the bullet cluster. It's two galaxy clusters have merged. And the pink that you can see, well, I'll just go back a bit. This is pretty relaxed, guys, here. The pink there is X-ray wavelengths where gases have mixed and they're emitting X-rays, and the blue is put in there because what essentially they've identified a lot of, I'll get my cursor going, there's a lot of gravitational lensing effect going on around here, and of course gravitational lensing, you need a lot of mass, and they can work out how much mass is needed to cause a certain degree of gravitational lensing effect. And where the blue is there, that's where there's a lot of mass, but you can't see any visible matter, so it's dark matter. So that's the bullet cluster, and it gravitational lensing effect that they identified is the evidence for some hidden matter in there, dark matter. So that's on there. And the cosmic microwave background, that's a whole exciting talk, which we'll do probably later this year as well. Okay, so let's move on. So there is Vera Ruben. So born in 1928, an American astronomer. Sadly, she died 2016, Christmas Day 2016. So she would have been there. She would have been, what, about 88? So, a full life. And you'll see there, I've put an arrow to an observatory high in the Atacama deserts in Chile. And you might say, why have I put that there, guys? It's because that observatory now is built in here on it. It's called the Vera Ruben Observatory, and it houses the Samani Survey Telescope. I think it's Samani, I think it's pronounced. And he was actually, David Samani was the chief engineer for Microsoft, who built the likes of Excel spreadsheet and so on. I only learnt that the other day, actually. So it's a primary mirror, about 8.4 meters, and it's a designed three-curved mirror, very similar design to the Hubble Space Telescope, whereby they get a very wide field of view with minimal aberration. So that's the advantage of it. Hopes to see first light in 2023, so that will be able to do some survey work. So that's Vera Ruben. So what made her famous, Nick? Well, she looked at a number of galaxies and measured the speed or velocity at which stars and gases were going around the center of their respective galaxies. And here's one in particular, the triangular galaxy was one of those, also known as M33. That's one of the three spiral galaxies in the local group of galaxies, obviously Milky Way, Andromeda, and Triangulum. I always remember M33 because the three is for triangulum. That's I always remember that one. So what she's done here, she's plotted on the y-axis the velocity of at which these gas and stars were going around as a function on the x-axis of the distance in light years out from the center of that respective galaxy. You can see 10,000, 20,000, 30,000, 40,000 light years. And of course, a light year has been the distance that light travels in a year, which is 10 million kilometers, 1 light year. So we're going out quite a way. Those spiral galaxies are all a decent size. And in theory, as you go out from the center, the velocity, because there's quite a lot of mass in here, the velocity of the gas in the stars should increase, and it increases up to here. Then in theory, if it's according to, you got less and less mass that you can see here. So in theory, they should start slowing down their velocity. They keep going around. And a very similar concept is the planets go around the solar system. The further you go out, the slower their orbits are, the longer the periods. But look what she discovered. The velocities kept going up and up and up. And when the graph in theory the velocity should be going down, it was continuing to go right up and almost starting to plateau further out there. So clearly what that indicated, there must be a lot more mass sitting out here in the outer parts of these spiral galaxies that we can't see. Because if the mass isn't there, it'll fly off. All those outer stars and gas would be flying off. The galaxy would not be stable. So that was a key piece of evidence, late 1970s, early 80s, of presence of dark matter around spiral galaxies. When you say dark matter, it's a matter that we just cannot see with light. Okay, so just let you know that it wasn't just a one-off galaxy with a triangulum galaxy. She did rotational curves for 21 spiral galaxies there. And you'll see the galaxies are all different parameters, different sizes, but the trend is there. You can see it. There's no drop-off velocity. The velocity just keeps going up and up and up for some time, and then it starts plateauing out. There's certainly no drop-off there. So, as I implied before, this whole business implies there's a large, probably 10 times as much dark matter as their normal matter surrounding spiral galaxies in this big halo you've got here. So was the implications of that discovery. So this was always, when I do my talks, excuse me, each month, you probably notice I always like to have a summary slide with some sticky messages. And the 3 sticky messages behind dark matter is, it's an elusive particle. They haven't identified it yet. Hence, it's very elusive. It doesn't obviously emit or absorb light, so they can't see it, so they've called it dark. And it makes up about 85% of all matter. So the other 15% of all matter is baryons, what you and I and sort of and our desk and our computers and everything around us is made of. There is compelling evidence for its existence. As I've mentioned, I threw back before 5 key lines of evidence. There is other evidence as well. And it's stuff that hold galaxies and galaxies clusters together such that they don't fly apart as they rotate around. So that's dark matter. That there is really the end of that section on dark matter. So I hope you found that valuable revision, a little bit of revision about dark matter. I should mention here, if you want to know more about any of these in more depth, just go to the AAS YouTube website and hunt down the relevant talk. They all get filmed, and you'll see the full talk on it. Failing that, if you can't find it, send me an email on that membership, astronomy.org.nz, and I'll send you the link to that talk. So that goes for any of these topics.
We had a quick question from Mike about the graphs you just showed there, Chris. He wants to know, why is the y-axis not angular velocity? Why is it a linear velocity?
Oh, okay, yeah, Mark, was a good question, Mark. So how they do it, it's radial velocity is what they measure with spectroscopy. So as gas or a star is coming towards you, it gets blue shifted with the Doppler effect, the wavelengths, and then it goes the other way as well. Now, you can work out angular velocities. It's a lot more involved because you've got to get proper motions as well. And it takes over numerous observations over a decent length of time to combine proper motion with your radial motion. So a Doppler effect with blue shifting of your spectral lines coming towards you, and when they're going away in the opposite direction, obviously on the other side of the galaxy, you get your red shifting. Now, if you want to know further about that, go and look up how I'm going to be talking about it. My next talk will be in April. March's talk is going to be on how we know the universe is expanding. April is going to be on how they measure distances. And they can look at water mazes, mega water mazes in some spiral galaxies where they can actually, particularly active galaxies with big supermassive black holes in the accretion disk, and they can track the mega mazes moving around, and they do that through a combination of radial velocity and proper motion to calculate angular motion. So good question, Mark. So that's the reason here. They did this in the 1970s, and it was done through radial velocities. That yes, it is possible, but a lot more involved. And this clearly gives them the information they needed. They didn't need to work out the angular velocities. Good question.
And then just a quick follow-up one from Mitchell, who wants to know, for dark matter, could the evidence potentially be explained by another hypothesis, for example, incompleteness in our current theories?
Yeah, depends where incomplete in your current theories. Well, certainly particle physics. The general consensus is, if you want to send me an email, I'll send you my little paper that I did on dark matter, and it talks about that. and then discounts all the other little possible things about it. Certainly looking at the cosmic microwave background and projecting that form with the cosmological model, it fits beautifully. All the figures stack up and allow us to see, accounts for the exact picture of how the universe looks today. So could it be machos, those massive halo objects that you can't see, like black holes and brown dwarfs? There's not enough evidence for that. It's all keeping with a particle. Particle physics we know is incomplete. In fact, all the particle physics models are all missing particles. They haven't yet identified hypothesized particles. And that's where there's different types of hypothesized particles, axions, neutralinos, and so on. Klein, all this Klein particles and so on. So Mitchell, send me an email at membership@astronomy.org, and I've done that together in a nice sort of paper about 23, 24 pages long, going over that exact issue. So do that, and it's a bit of a read for you, but good question. And I'll send you the link to the talk as well. So if there's it's more to do with particle physics that they don't know yet in terms of hypothesized particles. But you get your strino, someone who says, no, machos out there, don't believe it. But most people, and certainly myself included, researching it, it's a form of elusive particle. So good question, Mitchell. Now, question number 2, Einstein's special theory of relativity, demystified. That was one of our talks last year. So the question is, which of the below is a consequence of special relativity? Time contraction, time dilation, length dilation, unlimited speed of light, or maybe you stayed home to look after your cat that night. Maybe your cat was lonely and you didn't go to that talk that night. Though having said that, they're all filmed, so that's not really an excuse. I've just given you an out. So let's give everyone just a few minutes there. Okay, 1, 2, 3, let's go. The answer is time dilation. Did anyone get that, Steve?
That was Joseph and Mitchell who were hot on the triggers there. Oh, in fact, yeah, Mike's got it and Niven's got it as well. So yeah, we got.
Niven's in there too. Chocolate fish coming to everyone's way. That's excellent. That's good. Okay, so let's talk a little bit about the theory of special relativity, and it's based on 2 postulates, and it's a long story. And once again, it's in the handout and it's in the talk as well. And I go over what inspired Einstein to come up with these two postulates. The first is the laws of physics are the same for all objects traveling at a constant speed. In fact, that postulate had been around a long time. It was called Galilean postulate that Newton came up with, because Galileo and Newton both sort of said that when you're traveling on an aeroplane, for example, in modern times, obviously not their times, but our times, if you get happy and you jump for joy, you don't end up, wham, you don't get smacked on the back wall of the aeroplane. Is this, you jump up and you fall back down again. Same as when you throw a ball up into the air in an aeroplane. The ball doesn't hit the back, the back wall. It just bounces back down again onto your table or the floor. So the laws of physics are the same for all objects traveling at a constant speed. That's important, not acceleration. Now, here was the bit that he had some good insight, and just briefly, he got it from. He was the first person in history to take James Clerk Maxwell's equations of electromagnetism. There's 4 equations, and Einstein looked at them quite literally, and it's what those equations were telling him. Those equations were independent for any motion. There was no mention of motion, but the equations were accurate. So that went on, and then there was a couple of Americans, Michelson and Morley, in the US early on, and they did some experiments looking for the speed of light coming at different directions towards Earth at different times in the year, and they found there's no change in the speed of light. So Einstein this is where his brilliance was. He had the insight to realize, oh gosh, this is telling me something. The speed of light in a vacuum, roughly say space, is the same for all observers, regardless of the motion of the light source or observer. Now, that's a bit of a mouthful, so let's just go over that, and that's why I've got this nice little picture down here. So here's observer A. She's sitting on a red rocket and traveling at 90% the speed of light, and she's got a big light beam and she's blasting it ahead. And you would expect, Newtonian physics would say that, she would witness that to be traveling at 1.9 times the speed of light. This person on the blue rocket, she is traveling towards there at 0.8, sort of, so the 80% of the speed of light. Newtonian physics would say, well, they would observe the light. They're already coming towards it at 0.8, so it's going to be ultra fast. Sorry, actually, I made a bit of a mistake there. Newtonian physics would say she's already traveling at 0.9, so she'd see it leave at 0.1. And observer B would see it coming at 1.8 times the velocity. So that's observer B, and observer C would equally be affected by that as well. They would see it coming off here slower. But what Einstein says is that observer A, doesn't matter that she's already traveling 0.9 C and she's shining light in that direction, she still sees that beam of light leave her at the speed of light, irrespective of her own motion, irrespective of the fact that she's emitting the light. She sees the light leaving her at C, the speed of light. Observer B here in the blue rocket heading towards it, she also sees that light strike her at the speed of light, despite the fact that she's heading towards it. And observer C sees the same speed of light right across there as well. So that has quite profound implications. And here's a little story. So a little quiz for you. So you get Bob, and Bob's been training up to be a super athlete. And he decides he's going to try and outrun a beam of light. So he trains and trains, and the big day comes, and the stadium is just packed with people. And they shine the beam of light, and he bolts off and runs and runs and runs and runs and runs. And the crowd just go crazy. They see him. He runs to about 99% of the speed of light, almost gets there. So he's, the people in the crowd just go crazy. Wow, okay, he didn't reach the speed of light, but jeepers, he was hot behind that beam of light. So one of his mates go into the changing room to congratulate him and say he did. Poor old Bob's crying his heart out, crying into his glass of beer. What's wrong? What's wrong? Why was Bob upset? Because Bob saw the beam of light constantly leaving him at the speed of light. Even though he was traveling close to the speed of light himself, he still observed that beam of light traveling away from him at the speed of light. So as far as he's concerned, he didn't do very well at all. But from the crowd's point of view, he almost caught up with that beam of light. So it has interesting implications involving the entanglement of space and time. And it brings us on to the time, what they call the twins paradox of time dilation, how time is perceived. And here we have two twins. We've got Bev and Sue, both aged 25. Sue decides to travel to Barnard Star, about 7 light years away, at 95% the speed of light. So away she goes, and she leaves her twin sister Bev, aged 25, back at home. Sue gets there, turns around, comes straight back again. And when she gets back on return, Sue, who's in the spacecraft, has only aged 5 years. She's only 30 years of age. Bev, her twin sister, back on Earth, is 73 years old on Earth. So Sue didn't age much at all while she was away. Her clocks appeared to be going a lot slower. So you might think, wow, that's interesting. How does all that happen? So let's look into this. So there's a formula you can work it out. It's called the Lorenz Transformation. It's a general formula that applies to special relativity. And it looks all complicated, but it's not. And I actually go over in the talk. So once again, have a look through that. And if you can't find it, I'll send you the link. At the talk, I go over this. This is very, very derived very simply through right-angled triangles using a little, what they call a light clock, and Pythagoras' theorem. Very easy worked out. But the bottom line is the time that they say that Bev on Earth perceives Sue's clock to be running, observing Sue in her spaceship, is T0, which is the time measured on the stationary body. In this case, it's Bev's own clock on Earth. V is the velocity of the spacecraft, which was 95% the speed of light, and C is the speed of light. So you plug those values in there, and that tells you how the passage of time went. And it shows that when you're observing someone else in motion, their clocks appear to slow down. Now, two comments there. One is it happens even at relatively small speeds. When you hop in your car, that's happening. Hop in a plane and go to Sydney or whatever. That is happening then. But these are relatively small everyday speeds whereby it is happening, but the time difference is actually negligible. We don't notice it. But it's when you get up to speeds, the fractions of the speed of light, significant fractions, that you start noticing it in a big way. It becomes more and more apparent. And the other thing to mention is here, as far as Sue is while she's traveling, as far as she's concerned, her clock's going no different. She's standing there watching her clock. Everything seems perfectly normal. So that's why I throw the word in perception. It's Bev on Earth. It's her perception of Sue's clock that it's running slow. So let's delve a little bit more. So that was time dilation, clock slowing down when you're observing something in motion. But also when you observe something in motion, the length of that object appears, and that's the key to it, appears to contract. And the same goes if you're in that moving thing. So here's a person observing and a high-speed train's traveling. And very subtly, that train will appear to look shorter because it's in motion. If you're on that train, as far as you're concerned, everything's running normal. As far as you're at rest in that train, but everything else around you is zooming past. So the distances around you seem shorter, and that's why you get to a place a lot quicker, because you're traveling at a certain velocity, but even your distance is perceived to be smaller. So moving objects and distances appear to shorten. How much? Your Lorenz factor. Here it is here. So here's the length of an observed object. How much it shortens down to, you can work it out by this factor. This is the length of that train, for example, when it's standing still to you on the platform, and you put 1 minus velocity squared over c squared, and you get the length at which you observe it or perceive it to be. So it's the same formula. So the implications of special relativity is that space and time are not absolute. They're not separate. They are closely and irreversibly entangled into one identity. You can't separate them. They're just two sides of one entity. And that's what I've said here, is that time and length/distance for space are not absolute, but instead are relative to motion. Time appears to slow down when you're observing a moving object. Likewise, when you're observing a moving object, the length of that object appears to shorten. Now, a good analogy is something like a book. Here's a book, for example. It's got sort of yay width, yay length, and height, and so it's got those dimensions. Now, it's the same book. The book, as far as the book is concerned, does not change. But when you look at it, when the book's in motion, turning relative to what you see, every quick snapshot, so to speak, if you will, blink of your eyelid, you're seeing a different view. The book looks different, but it is the same book. And say, for example, you had that for space, and that's time. For example, if I started turning, you'd say, oh, space is getting shorter, but time is getting longer. But as far as the book's concerned, time was constant, space was exactly the same. It's when things start to move, particularly closer to the speed of light, people's observers' perceptions of them change. So, yeah, a lot of things confirm special relativity. Atomic clocks on planes, they've flown them at high velocity and found they tick slower than the clocks on Earth. Our GPS satellites are all programmed to allow for that, for their motion as well. Your electronics, your TVs, your watches, your mobile phones, they are all part of the design. Is the calculations are built in there to allow for special relativity. And without that, they wouldn't work properly. So that's sort of pretty much proof. Because, of course, the whole purpose of when you come out with a postulate, then you try and work out the implications of your theories, the theory that's come from your postulates, and then you try and predict things and then show them in experiments, and that confirms your theory. So there's the muon paradox is really cool. So what are muons? Muons are subatomic particles that get created in the upper atmosphere when high energy cosmic rays, so high velocity particles come in from outer space, often helium atoms and stuff, alpha particles, collide with particles in the atmosphere and create these subatomic particles called muons. Muons then travel through the atmosphere at about 98% of the speed of light. And the mean lifetime of a muon is very, very short. It's only about 2.2 microseconds, which means the time it would take them to reach the ground is about 15 times their mean lifetime, which means, yeah, you don't get many at all. So Newtonian physics predicts you get negligible, if any at all, muons would eventually reach the ground. They just don't live long enough to travel that relatively large distance for them, sort of 10 plus kilometers. So, but in actual fact, appreciable quantities, quite large amounts of muons are detected in the detectors on the ground. Why? It's because of special relativity, time dilation and length contraction. So from our perspective on the ground, looking for these muons, or watching them, if you will, the muons clocks are ticking a lot slower. So the muons are living longer and hitting the ground. But as far as the muons are concerned, their clocks are ticking fine, but we perceive them to be ticking slower, and they live longer and get to the ground. From the muons' point of view, their clocks are ticking okay to them, but their perception of, because they're traveling so high speed, they look at the distance between them and the ground, and it's actually a lot less. So that's their perception, is that their clocks are ticking normal, but they don't have to cover much distance to reach the ground. So you've got time dilation and length contraction going on there, and that sort of all is in keeping with Einstein's special theory of relativity. So does that, any questions there, Steve?
No questions, but there's a comment from Mitchell who says, for those wondering, the paradox, the twins paradox, disappears when you consider the acceleration of the one in the rocket, and then Mike clarifies accelerating and non-accelerating reference frames.
That's how the paradox works. That's the solution to the paradox. It's exactly the person in the rocket, Sue, has to decelerate and accelerate again. So it's worth looking up, guys. Yeah. So the sun, another one of the talks was the sun, our nearest neighbor, what's going on and why. So, that's just pictured a little bit of humor there. Let's move on. Okay, so in what order are the three inner zones of the sun? A, the radiative zone, the core, the convective zone. B, the convective zone, the core, and the radiative zone. C, the core, the convective zone, and then the radiative zone. And of course, we're moving from the inside out. I should make it clear here. D, the core in the middle, the radiative zone, then going out to the convection zone. Or maybe you were at the talk, but you fell over and got tired and slept in the back row. Who knows? So that's your out for the night. Okay, so once again, just give a few minutes here. And so those are referring to moving from the inside of the sun out towards the surface of the sun. No. Yep, and I hope no one put A and B. It was pretty clear that it started with the core. So yeah, it's the core, the radiative zone, and then out to the convection zone. So how did everyone go on that one, Steve?
Yeah, it was Mike this time who was in first with D, but then got quite a few with the right answer. T. Malik, Mitchell, Anne, Joseph, and Jakuma all got the right answer.
Go, guys. Cool. Excellent. So let's talk about the model of the solar interior zones. So the core here, where nuclear fusion of hydrogen to helium occurs, that goes out to about 25% of the radius of the sun. And it's because the huge weight and mass that generates the gravity towards the core of the sun raises the temperature up to about 25 million degrees Kelvin. And that's just enough, with a little bit of help, of course, from quantum tunneling. That's another story, which we talk about in the full talk. But the bottom line is hydrogen gets fused to form helium, releases energy. 99% of the process is via the proton-proton chain. About 1% is via the CNO cycle. 600 million tons of hydrogen get consumed per second in the core of the sun. Check that out. So the product of that hydrogen fusion, of course, is high energy gamma rays, so high energy photons, the highest energy ones in the form of gamma rays, and solar neutrinos. And it's the solar neutrinos, the detection of those in certain numbers on Earth, that provides the real hard evidence that indeed the nuclear models are correct and nuclear fusion is behind in the core of the sun, is what's behind what powers the sun. And once again, if you want a copy of that, I did a write-up on that as well. Just on solar neutrinos, solving the solar neutrino problem. Feel free just to flick me a quick email and I can fire that out to you. That's sort of one of my little pet subjects. Okay, so then, all the gamma rays get produced, and then they've got to work their way through the radiative zone, and that goes out to about 70% out into the radius of the sun, and the particles are so densely packed in there that the gamma rays can't just freely travel through. They're constantly being absorbed by particles and readmitted again. The particles are just jam-packed, so dense, and it's so hot in there. They're so energetic. They're running around like crazy. And your little gamma rays only get to travel just such a tiny distance. They get absorbed by a particle. The particles zooming around instantly, or close to instantly, emits the gamma ray back out again. And that whole process is such that photons take about 170,000 years to be absorbed and reemitted again, zigzags, to get to out this far to the other side of the radiative zone. The temperature ranges from about 2 million degrees sort of out here through to about 7 million degrees, sort of where the inner part of the radiative zone meets the core. So now we move out to the outer end, to the convective zone, and that of course goes out to the surface of the star. And it's much less dense. Average temperature is about 500,000 degrees Kelvin. And what happens here is you've got the energy is transferred by what they call convection cells, whereby you get packets of hot plasma, which is your charged particles that go to make up the material in the sun. They heat up at the bottom of the convection zone, or the outside of the radiative zone. And of course, when material heats, it expands, and when it expands, it becomes lighter. And it slowly drifts up towards the surface of the sun, gets rid of its heat in the form of photons, once again, which by now are, and you guessed it, optical wavelengths, so much cooler wavelengths. And as that material releases its heat to the surface of the sun, it cools down. When it cools down, it shrinks. When it shrinks, it becomes less dense, more dense rather. And of course, when something's more dense, it starts sinking back down again to the bottom of the convective layer. And that's a continuing cycle of heating up, rising to the top, getting rid of your heat and coming back down again. It's exactly the same process that occurs when you boil up your jug of hot water. So those sort of cells, if you will, convection cells, they travel at about 500 kilometers per second. It takes about 10 days for those, for the heat to slowly rise up through that convective zone. And the surface of the sun is about 5,800 degrees Kelvin. So just a brief summary then, you've got your core, which goes out to about 25% of the way up of the radius. The radiative zone goes out about 70%, and then out to the surface with the convective zone. And as we've mentioned here, the end result is you've got these gamma photons, really high energetic gamma photons that get produced at the core from the hydrogen fusion. And by the time they leave the surface, they've cooled down a lot, down to the optical wavelength photons. Yep, it takes 170,000 years for a photon to work its way through the full size of the sun, the interior of the sun, but it only takes 8 minutes then for a photon of light, because of course it's in a vacuum of space now, travels at the speed of light, and it only takes about 8 minutes to get from the sun to the Earth. How do they know all this sort of stuff? Well, a couple of things. One is there's models. They roughly know what the temperatures would be and what the conditions would be. So they try and draw up sort of models with the known physics of what they expect things to be. But also in that convective layer, there's a lot of tuning going on. And you could well imagine there's a lot of acoustic pressure waves that get generated in that convective zone. And then they reverberate right throughout the interior of the sun, and which in turn gives rise to isolations on the surface of the sun, which they're able to record by helioseismology. So they point spacecraft at the sun's surface, specifically looking for little isolations in the surface of the sun. They analyze those. It takes supercomputers, but they work out little patterns. And those models that they generate from that reflect the internal surfaces and the dynamics that are going on in the sun. And they do match up nicely with the solar sort of models of physics. And also the solar neutrino experiments confirm that they detected the neutrinos they needed to see and exactly the right numbers to allow for what they thought was going on in the right amounts inside the sun. So that's the sun. Any questions there, Steve? Are we all good there?
Yep. No questions for that one.
Cool. Yep. So, so the night sky. What are we looking at as a talk? So, as I said here, a lot of us look. You might be camping in the dark somewhere, on the boat in a bay somewhere, and you look up at the night sky. You think, "Jeepers, that looks beautiful." What are we looking at, guys? So throughout the whole talk, I talk about looking at the constellations, galaxies, planets, how you separate planets from stars and stuff. So once again, look for that, or you're welcome to flick me an email or send you the link in the handouts and stuff. So of course, I've just tuned in on looking at stars. So stars that are visible to the unaided eye at nighttime are A, predominantly main sequence stars, B, predominantly late stage stars, C, number about 500. We're talking a clear night here, sort of way up in rural New Zealand on a beautiful clear, no wind, no cloud, no moon, no city lights, beautiful stargazing conditions. Or D, number about 2,500, or E, B and D, predominantly late stage stars and about 2,500. Or sorry, I went to the talk, I got my handout notes, but the dog ate them, and I went to look for them today, but the dog had eaten them, so I'm unsure. So, yeah, what's okay? I'll just give you a few minutes there before we bring the answer up. There we go. I'll take B, D, or E, because both B and D are correct.
Okay, Mike was the first one to answer with E. T. Malik answered as B first up, and then Joseph Mitchell and Anna and Rufus all also got the right answer.
Cool. Oh, we're getting some more people coming on board too. Welcome, guys. This is cool. It's all good fun. Yeah, so let's look at it further. So there are some things about stars to consider. So first of all, yeah, it's about 2,500 stars off the Milky Way. Almost, pretty much all the stars that you look up as individual stars with the unaided eye are all part of the Milky Way galaxy. And those of you say, well, how about the Magellanic Clouds? You can't really see individual stars in the Large Magellanic Cloud with the unaided eye. So for all intents and purposes, all the stars you're looking up to are all in the Milky Way galaxy. And there's things about stars to consider. Stars differ in their size, their brightness, and their relative numbers. Stars evolve and change their appearance. So which begs the question, so which ones are we looking at with our unaided eyes? We're not talking big telescopes here, zooming out and zooming in on things and seeing sort of fancy dim stuff. We're talking here with the unaided eye. What are we really looking at when it comes down to the stars? So let's just do a little bit of revision on stellar evolution. Yep, stars are born, they evolve, and they die, like a lot of things in nature. So just recapping, you get these huge big molecular clouds of gas and dust, and you get little regions of them that start condensing down into like little knots, and each of those become stars, and you get numerous stars from each big sort of cloud called a stellar nursery. And then they get split up into stars that are less than 8 solar masses. A solar mass refers to the mass of our sun, which is roughly 1.99. Say this, call it 2 times 10 to the 30 kilograms. So we either split them up into stars less than 8 solar masses or stars greater than 8 solar masses. Stars spend 90% of their lifetime sitting on what they call the main sequence. And that is the state of when stars are in, when they're burning hydrogen in their core into helium, just like that model of the sun that we just saw. So that's where stars spend 90% of their life in a nice stable state, burning hydrogen into helium at their cores. And by definition, when they're doing that, they're called what they call on the main sequence. So they spend 90% of their lifetime there. They then evolve off that when they run out. That's a whole other talk again on the details. But they eventually, all good things come to an end. So there's hydrogen in the core, and they start to swell into red giants and red supergiants, respectively. The sun will swell out to about Earth's orbit when it eventually does its dash. The sun, probably about 10 billion years for its main sequence lifetime, and about halfway through there. So we've got a bit of time to go yet. And then there's what happens then is they get to a certain size, and then the outer layers start to just gently puff out like that, and you get these beautiful, big ionized planetary nebulae. You've probably seen loads of pictures like that, because what's happening is that the core gets exposed, and that's caused very, very hot. It's a carbon-oxygen core, very, very hot, sending out hot ultraviolet light, and that ionized, which causes all the gas and dust that's puffed off to fluoresce. And then, of course, you get the white dwarf, and all that sort of stuff is all eventually dissipated over a few tens of thousands of years. You're left with the exposed core, and it's called a white dwarf. These larger stars, greater than 8 solar masses, they become what they call supergiants, much, much bigger. And at the end of their lifetime, they explode massive explosions called supernova. If they're between 8 and 20 solar masses originally, the core gets left as a neutron star. And if it's greater than 20 masses, the core gets left as a black hole. We've done talks on all of these. This is just really to bring up the terms and help put things in perspective for you. So there's probably a few things here you might say, okay, I think I've got this. So main sequence stars spend 90% of their time in main sequence. So 9 out of 10 stars, all that should be there should be main sequence stars. Yes, the stars that are out there, but not necessarily what you see, because there's some catches coming up. And the other thing you would have picked up here is that giant stars, giants and supergiants, are much larger and brighter. So that should also give you a clue that maybe they make up a bit more than 10% of what we see with our eyes. And so let's move on and have a look at that. So let's focus on the main sequence stars that make up 90% of stars that are out there, not that you can see, that are out there. They're classified by what they call their spectral class, and that's defined by their surface temperature, which also relates to their colour. It's like a flame. A cool flame, for example, is sort of an orangey colour. You heat it up even more and more, and the flame gets sort of white and blue and so on. So it's their surface temperature and how big they are and how luminous they are, or their brightness, in other words. And there's sort of some groups here, for example, down way at the very bottom here, you've got M and K class stars. They're called red dwarfs. You get different definitions of red dwarfs, by the way. Some people say just a K for red dwarfs, and some people say just the M's, and some people say K and M's. I've gone for K and M classes. I've labelled them as red dwarfs, which is not uncommon. Surface temperature, about 3,000 degrees. Our sun is a G class. Surface temperature of 5,800, which we saw in the last question there. Sirius, the Dog Star, you see the brightest star in the night sky. And for Canis Major, that's an A-class star, and it's got a surface temperature of about 10,000 degrees. And then you've got the huge, hot, large, and bright O-class, which sort of get much huge temperatures again. So they are classified by their size and brightness and their temperature, and split into what they call spectral classes. You might say, check out that alphabet, man. Woo! M, K, G, F, A, B, O. What's going on there? When I went to school, the alphabet started with A and went A, B, C, D, E, F, and G, and so on. What happened was they did do that when they first started identifying stars. They labelled them A, B, C, D, and so on. But it was based on the strength of the hydrogen spectrum with their spectroscopes, how much hydrogen, because they didn't really understand what was going on in stars. So they thought, well, here's the hydrogen spectra. We'll just classify them there. And then, of course, as they learnt more about stars, they realised, that's not the way to order them. You order them in terms of their size and their brightness and their surface temperature, but they kept the original set of letters with them. So it's for historical reasons. So just in case you're wondering, that's why. Okay, so let's move on. So they don't all come in equal numbers. So look at this graph here. So this is called the initial mass function, or IMF, and it tells you the fraction of different sizes of stars, main sequence stars. Nature always has a bias of producing smaller stars, such that there are exponentially more smaller stars than large stars in the universe. So, for example, here, look at this. Here's your red, which is your M class, make up, say, almost 76.5% of all stars are the M. Here's your Ks, K class, 12 right there. So that immediately tells you 90% of main sequence stars are K and M class red dwarfs. Check out this. The O class is 0.0003%, tiny, tiny, tiny whisker. You can't even see it on the pi diagram. They've just sort of had to draw a little bit of an arrow to it. And then the same with your B class, 0.13% of all stars are those hot B classes. So they're a slither you can just make out there. The A class only make up 0.6%, your F class 3%, and your G class, which is our sun, make up about 7.6% of all the stars in the main sequence. So the bottom line is there's exponentially more smaller stars in the galaxy than there are larger stars, whereby the larger ones are just so damn scarce. And 90% of them are all these red dwarfs. So what are the implications of that? Well, the bottom line is, when it comes to viewing the night sky with the unaided eye, your K and M class red dwarfs are just too cool, too small, and too dim to actually see. You can't see them with the naked eye. You need a telescope to actually see them. The nearest one to us is Proxima Centauri. Your naked eye, you can see the Alpha Centauri, of course, star complex, but you can't see Proxima Centauri, which is a red dwarf, which is the closest star to Earth, about 4.2 or something like that, light years away. And despite it being the closest star to Earth, it's a red dwarf. Can't see it. Barnard star is actually the same too. So let's move on. So you can't see them. So that you immediately culled out 90% of your main sequence stars you can't see with the naked eye, the unaided eye. You've immediately culled out them. But check this out. The A and E, B classes, which are so hot, so large, and so bright, they must be so easy to see. But they're just so rare. You can't see, there's just so few of them out there. So when you do see them, you think, wow, that's pretty rare. And there are a few of them out there. They're not totally off the radar. But also augmenting that the fact that there's so few of them, they're actually just so short-lived before they go to supernova. And I'll show you this. The bigger the star, the bigger the mass it is, the bigger the gravitational forces coming down on the core, so the hotter the temperatures are, so it burns through its hydrogen a lot quicker, whereby there's a principle. Large stars burn through their fuel exponentially faster than smaller stars because of that. And here, look, here's a star here. These are the massive stars up here. Here's your solar masses. The sun, one solar mass, your G class. You go up to these 25 25 solar mass stars with O, spectral class O. Then you go over here to the main sequence lifetime. Here's the Earth, the sun rather, about 10 to 12, they've got here quoted here, 12 billion years that it expends on the main sequence. So we're about halfway through it. But look at this one here. If you had a 25 solar mass O class, not only is it the rarest hen's teeth, there's not too many of them around, but they only live such a short time, 4 million years, such that the lifespan of our G class sun is on the main sequence is 3,000 times longer than an O class main sequence star. Crazy, isn't it? Yep. So that's why you're not going to see too many of them. So you can already see where this is heading. It's all not what it seems. So the bottom line is it's these three classes here, your G, F, and A, that can be seen if they're close enough to Earth, usually up to tens of light years with the unaided eye, like 10 or 20 light years away from us. You can see those G, F, and A classes with the unaided eye. But these ones here, there's zillions of them. There's 90% of them that are too dim to see. And these guys up here, they're so bright, and you'd think easy to see, but there's so few of them, and they just live such a relatively short time. So that's the main sequence stars. Hopefully you got some messages there. How about these giants, red giants and red supergiants? Let's have a look at these. Because as we pointed out here, these stars swell out, whereby, for example, they get so big, I mentioned to you, the sun will swell out to Earth's orbit. And these Betelgeuse and Antares, which I've got some pictures coming up shortly, they are much larger and brighter than this. They're supergiants. And if you put Betelgeuse in the middle of the solar system, it would go out to about the orbit of Jupiter. That's how big these babies are. So, yep, they swell late in life. They become very bright and easy to see. There's actually a typo here. Both Betelgeuse and Antares are red supergiants. Aldebaran and Arcturus, they are both giants. I will change that. So these are the two readily visible supergiants in the sky, Betelgeuse and Antares, that can be seen at much greater distances, thousands of light years away from the unaided eye. So they're just so extremely large, and they make up a large number of the visible stars. So you've got the principles now of main sequence stars. You can just see the middle of the road ones relatively close, but these supergiants and giants are much further away, but they are much and rarer, but they're so much easier to see. So let's have a look here. So this is a histogram showing you the percentages of visible stars according to the different types. Here's your main sequence. It's roughly 38% of the stars you're looking into the night sky are main sequence stars. And you know that predominantly they will be your G, F, and A class. Your giants, there's some subgiants here, and your giants and your supergiants here make up about 62% of the stars you can see. And of course, you may say, what's the difference between the giants and the supergiants? Remember, the supergiants came from those big sort of those big O and B class stars. They're so rare, there's not many of them, so it makes sense you're not going to see many supergiants, but they are out there and they're really, really, really big. Your giants are from when your stars more like your up to 8 solar masses. There's much, much more of them. So in summary, most stars observed with the unaided eye are subgiants, giants, and supergiants. Stars in their late stages of their life, that makes up 62% of the stars you're looking at when you look into the night sky. 38% are middle-aged main sequence stars that are moderately close to us and moderately bright. The others are not bright enough, or they're too scarce to see. So that's really the little coverage of things to consider when you're trying to work out what sort of types of stars you're looking at with the unaided eye. Any questions there, Steve?
Yeah, so you sort of partially answered this, but Mike wants to know, has the 90% K&M main sequence stars been constant over time, or is it reflected of us being 14 billion years past the Big Bang?
Oh, okay. For new star formation, like for example, if you do a survey in the Milky Way right now, snapshot, those are the figures you would see. And also it all comes down to, so I get what you probably mean. They live longer lives. They do live longer lives, much longer lives. Is it a factor of there? The main thing is a thing called the gene length, whereby when those large molecular clouds start sort of breaking down into little not stable knots and so on, the smaller distances are more stable and more likely to fall into stars. So is there a larger amount of them because historically they live longer lives, so they're going to hang around longer? Possibly. But the main reason for it is nature definitely has a bias producing much, much, much more stars in smaller proportions. But yeah, that's an interesting question. So those figures, of course, are taken by a snapshot of the galaxy as we see today. So there may be a factor in there. I get where you're heading with that. But having said that, you could also argue when those big stars go supernova and explode, which they do early, all that product of the supernova explosion gets reseeded back into the next generation of clouds to make another big batch of stars. And that next generation of stars is going to have exponentially more and more smaller stars, of new smaller stars too. So I think the prime reason for it is, yep, nature has a strong bias. It all comes down to stability, and it's to do with gravity and the velocity at which things rotate. It's called, Google up the gene, G-E-A-N. There's an astronomer by the name of Gene. He did all this initial research on it, and there's the what they call the gene length, whereby it's the optimal length at which sort of tends to create that bias. So good question. Okay, so
second question, if you got time.
Yep.
Anne wants to know, how did the 8 solar masses get selected to be the distinguishing point between large versus small stars?
Yeah, sure. And yeah, there's, of course, it's not 8.0. Oh, look, that star's 8.1 solar masses. That's going to go supernova into red supergiant and so on. And oh, that's 7.9. There's a lot of crossover there. It's just a fuzzy line, and it all comes down to the physics of it all, because we don't see stars. We've only been looking at the stars for a few hundred, 200 or 300 years, so we haven't been able to see them go ahead. But it's the laws of physics. They say, look, roughly when you get about 8 solar masses in there, let's just go back to that slide. Yeah. So when you get to about sort of 8 solar masses here, you're going to go into sort of a red giant. And there was actually, we did a talk on, a whole talk on this, on stellar evolution. But the physics, they got it pretty down pat. The models of stellar evolution have been very, very successful. And red giants are different to red supergiants, whereby these ones go up what they call the red giant branch, the horizontal branch on the Hirschsprung-Russell diagram, just to Google that. Then they go up what they call the asymptotic giant branch. And it's during that the outer layer starts to shred off to create this planetary nebula. You don't get to see that down here. Now, and you're asking the question, why is it cut off? The bottom line is it's not a cut off. There's a fuzzy area in there. But it's around that sort of let's, for example, if you said 7.5, what's that going to happen? The models of physics, astrophysics, definitely say something 7.5 solar mass is definitely too small to turn into this. It's going to go through this down this line here. Equally, if you had one, say 10 solar masses, it's going to go down line this here. And I think they just worked out statistically it's probably around the 8 solar masses, so you just run with that. You sometimes will look up a paper and they've seen a supernova and they've gone backwards and they've worked out what its progenitor, that's sort of the original star size, in other words, and they've said, oh, look, we think this was, an 8 solar mass or something like that, or just below it. And you think, oh, I thought 8. It's not exactly 8. So it's just, there's a bit of a fuzzy line in there, but the stellar models sort of draw the line. It's around the 8 solar masses. And I suppose in answer to your question, it's based around astrophysical models, computer models of what's going on inside stars, knowing their conditions and the laws of physics and heat transfer, nuclear energy and so on. And it certainly seems to match what they observe. So I hope that answers the question. It comes down to stellar modelling, which has been very, very successful, and it's not on the line of 8 solar masses. There's a fuzzy patch in there, I'm sure.
It's just a quick follow-up from that diagram, actually. So you're going to stay on that diagram. This is from Jai Kumar. I'm not sure if I'm pronouncing that right. But they say the diagram suggests that the white dwarf and neutron/black holes are determined by size, the 8 solar masses, but don't white dwarfs become neutron stars or black holes when they're above the Chandrasekhar limit? Okay,
so they all become here. White dwarfs come from, it's the core left over from a less than 8 solar mass eventually. And the same with neutron stars and black holes. So what you're referring to in a binary system, different story, well, similar, but a little bit of a twist to the tale. If you get a white dwarf in a binary system with a red giant or red supergiant, the material can get siphoned onto the surface of the white dwarf. You can get repeated explosions of hydrogen fusion on the surface, which create what they call nova. And go and look up my talk. Once again, you're welcome to email me and I'll send you the link to it. I did a whole talk on novae, supernovae, and hypernovae. What's the difference? And I've also got one here on stellar cores. The party's not over. And send me an email if you like, and I'll send you the link to those 2 talks. And with handouts, no, there's not handouts for those. I did them both online. And the particular one, stellar corpses, the party's not over. And I meant it exactly that. The party is not over with these stellar corpses. They get up to all sorts of mischief. But it's in the context of a binary system. Sometimes that's, if you get enough material, accumulates onto the white dwarf. And you're quite right. The white dwarf has a mass limit of 1.4 solar masses, and the 200 limit, whereby if it gets heavier than that, because it's in a state of degeneracy, electron degeneracy, that breaks down and you get runaway nuclear fusion, and you get a massive explosion, a type 1a supernova. And I've got a whole talk as well on all the different types of supernova, which I can send you. But it's a thermonuclear reaction, which is different to this supernova, totally different. It's a really much, much brighter one, so bright they actually use those explosions to measure distances to the far ends of the universe, which I'm going to be talking about in 2 months' time. So that's what you're talking about there. So it still holds. You end up with a white dwarf up to 1 solar masses. You end up with a neutron star if the progenitor was 8 to 20 solar masses. If the progenitor was greater than 20, you'll end up with a black hole. Once again, with a similar covenant to what we just spoke about, these lines aren't straight lines drawn in the sand, a little bit of fuzziness, but the principle is there and they match the observations. So that still holds. But yeah, what you have ranged is those guys get up to all sorts of mischief and trouble. And the same with neutron stars, the same with black holes. You put them in a binary system with a red giant or red supergiant, they siphon material off, form an accretion disk, and all sorts of really fun things starts happening. But particular, as you allude to, with the white dwarf gains the mass, becomes unstable, and it blows itself apart. Now, it doesn't form into a black hole. It just totally annihilates itself, blows itself apart. It hasn't quite got the mass to go into a black hole, and the explosion just rips it. It's gone. It's finished. So hope that answers your question there. Good question. Two good questions. Let's move on to star clusters, open and globular clusters. So different but so similar. So let's just briefly here concerning star clusters. A, open clusters are young. B, globular clusters are old. C, open clusters are in the galactic disk. Or D, globular clusters are in the galactic halo. Or E, all of the above. I'll give you a few minutes just to decide on that. Okay, here we go. All of the above. So I'll take A, B, C, D, or E, preferably E, but if you put one of the other ones down, you are right. How do we go, Steve?
Most people have picked E, so Mike got in there first, followed by Anne and Joseph, and then there's a few more following in. T. Malik and Jai Kumar all got E. Well done.
Whoa! Yeehaw! So, guys, you've been obviously watching the talks and stuff over last year. That's fantastic. And yeah, lots of chocolate fish and chocolate goodies and treats. Obviously, I'll need to bring a Santa sack full of them, I think, when we start doing our live talks. So let's move on. Let's talk about open. So open clusters, briefly. Who can name this cluster? This is a beautiful cluster in the southern sky, close to the Southern Cross. It's called clue NGC 4755. Can anyone name that cluster? I've given you so many clues there. Any takers? Doesn't matter.
Yeah, Mitchell's got in first with the jewel box.
Whoa, good work, Mitchell. Okay, yeah, we'll talk about that in a minute. So, yeah, what open clusters are, they are just a few, like 100 to a few hundred, very young, recently formed stars that are formed all from the same molecular cloud, and they're all loosely gravitationally bound together. So you get a molecular cloud, you get a whole stack of stars formed in those first few million years. They're all hanging together. They're all siblings, same proximate age and composition. They all hang around together. So 100 or a few hundred of them are there, and they move through the galactic disk because, of course, they're associated with star formation, where you see star formation, and then eventually with gravity they start to disperse. They get into gravitational perturbations occur, and they slowly wander on their way. They get disrupted by other clusters, and clouds go through them, and that's what disperses them. Typically, they live up to about sort of rather across size-wise, about 30 light years across. Typical. They vary a little bit, but that's your sort of typical sort of open cluster size. So they are a loosely gravitationally bound collection of young stars in the galactic, which I put here, disk. I'll show you a picture of the disk going along there and there. As opposed to, okay, there's the spiral arms, where active star formation occurs, and it's the jewel box, as Mitchell was saying. It's about 100 stars and about 16 million years old. If you haven't seen the jewel box, you can see it with the binoculars, but I'm going to show you where it is right now. Really spectacular. Otherwise, your telescope, or next time you see a telescope, say, hey, can we have a look at the jewel box? It's beautiful. You see, rubies, emeralds, all sorts of colours. They're all these young, beautiful, bright stars blazing away. They're all different colours. Why different colours? Different surface temperatures. So here you go. Here's your Southern Cross, pointing towards here. Here's your two pointers. There's the longitudinal axis of the Southern Cross. And it's the second brightest star in the Southern Cross, or the one closest to the pointers, and just inwards towards the pointers, just a little bit there, and that's where it sits. You usually find with the binoculars, or even with your finder scope, it's pretty easy to find. You just go hunting around here, you go in a little bit towards the pointers from the star here, and you'll find it. It's beautiful. So globular clusters, totally different, aren't they? So what they are, you got much more stars. Instead of being young stars, they're much older stars. Instead of just a few of them, you got up to millions, more of them. Instead of being loosely gravitationally bound and start to disperse after a few million years, these guys are really tightly bound. And, these are up to 11 billion years old. So they formed early on in the universe. And I go through on my talk on clusters. Late last year, I talked about how the current theory is how globular clusters formed from these big superclusters. So globular clusters are much larger, more compact, older, and more stable than open clusters. This one here is 47 Decanae. It's the second brightest globular cluster in the sky. The brightest one, of course, Omega Centauri. It's about 13,000 light years away. That's looking back south in the sky too in the summertime, so that's lovely. It's about 120 light years across, to give you an idea. And they've positioned here in the halo. So here's your disk where you get your star formation and naturally your open clusters here. Young stars, the globular clusters, really old stars, sort of 10, 11 billion years old, tightly packed millions of stars. So if you go to the original talk, you'll see there the current theory of why they think that is so. That's interesting. So there's over 150, possibly up to 200 globular clusters in the Milky Way. Most galaxies have series of clusters. There's a whole science around globular clusters, and they give you a lot of information. You can look at them and study them. They're all different orbital mechanics or sort of orbital dynamics and slightly different compositions where you can work out where they all belong to separate galaxies in the past, dwarf galaxies that collided with the Milky Way. And they can do a lot of archaeology, if you will, of the formations of the Milky Way by analysing the globular clusters. So that's quite cool. I thought I might do a sort of a bit of a talk on that whole concept at some stage this year. So the sixth and final question is about the talk we did on liquid water on Mars, a story of climate and change. So here's your question. The Curiosity rover landed where on Mars? A, Meridiani Planum, B, Jezero Crater, C, Gustav Crater, D, Gale Crater, or E, Lyceum Planitia. So I'll give you a few minutes for that one to Google search it. Okay, so hopefully people will know that. Okay, and the answer is Gale Crater. Did anyone get that there, Steve?
Yeah, Mike got that one right.
Mike's on fire tonight.
He is indeed.
Okay, so A, with Meridiani Planum was where the Opportunity rover landed. Perseverance, the most recent one up there, that's in Jezero Crater. Spirit rover, the rover was the same time as Opportunity, that went to Gustav Crater, and of course the InSight lander to look at the inner structure of Mars, its crust and so on, looking for Mars quakes and stuff. That was landed in Elysium Planitia. So let's have a look at Gale Crater. So I've put here actually the locations of all these landings here. What do you notice about them? They sort of have a bias, don't they, for a sort of equatorial type of latitudes. So here's your north sort of pole up sort of region up here, and here's your southern area down here in this sort of thing they've flattened out. It's a topographic map where blue is lowland and the redder the tone is the higher. And you'll see there's a crustal dichotomy going on in Mars, how the northern plains, once again, they're very smooth, relatively smooth, and the very lowlands, so the northern lowlands there. And the further south you get, you start to get into the southern highlands where higher altitudes, and it gets more cratered and pitted. And you can go to my talk on water on Mars. Once again, that was a whole separate talk. You can either go searching for it, or if you can't find it, just email me the membership. I'll put that email on again shortly. Email me and I'll send you the link to the talk. But you'll see, look here, look all these. So here's Curiosity and Gale Crater. There's your InSight, Spirit, Opportunity, Pathfinder, Viking 1 and 2, Phoenix is up there. So the reason behind that, it's a trade-off where you want to look. Ideally, it would be lovely to get up here and have a look at all these highlands and craters, but Mars's atmosphere is already so thin, and if you're up high, the atmosphere is thinner up there as well, and you haven't got a lot of atmosphere to come down and land. And your northern area would be perfect place to land because it's lowland, so you've got more atmosphere for your parachute to come down and slow down, and of course the atmosphere gets thicker the further you go down. So you've got more atmosphere and thicker atmosphere to control your landing. So there's definitely a tendency to go further north. But the other thing they tend around the equatorial ones, though, is because all the interesting geology between the sort of crustal sort of dichotomy that's going on here is in those equatorial regions. They're close. There's some volcanic. You can see there's been past volcanoes here. All sorts of interesting features here. And so they're getting sort of reasonably old surfaces here to look at the history, because this is very young sort of lowlands up here, relatively smooth surfaces. So if you're gonna get only so much information, the further you can go back in time, the more information you're going to get. So they're trying to go back up into here. But so in the middle equatorial regions is a nice trade-off, if you will, between the engineering side of landing with altitude and purposes of geology. So Gale Crater. So this is Gale Crater, 154 kilometres across, and that's about a little over 3 times the size of Lake Taupo. And I've actually got a slide coming up shortly that I'll put Lake Taupo beside it to show you that. But I just thought I'd show you the dry patch bit first. And it's got Mount Sharp in the middle, big mountain about 5.5 kilometres high. And that mountain is multiple layers of sedimentary deposit over millions of years. So that in itself, as you can imagine, going up that Mount Sharp, you're able to sample rocks and minerals from different time period, different epochs on Mars. So that is just a bank vault of information. The other thing they chose it here, and they landed here obviously in the flat bit, they didn't want to land up in the hills. They landed in the flat bit because Gale Crater's got a lot of inlets and outlets of water that you can see sort of here's some obvious ones here trickling through. And it's got lots of deltas or alluvial sort of areas, alluvial fans, and that refers to when sediment comes washing down a stream or river and it goes here, and there's all the sediment gets laid, like a sort of a delta, if you will. They call them alluvial fans at this sort of type of thing here. So they landed in here so they get an idea of the minerals that would have been, hopefully flowing down in rivers and stuff, if that was so. And then, of course, they can traverse up this beautiful mountain here, just full of sedimentary deposits of all different times, different epochs. So it's just a lovely place to land a rover. What did they find here? There's evidence for large lakes and changing climate. There's a lot of sort of aqueous sedimentary rock here, consistent with having formed in water. Mainly that was mudstones and sulfates, and there was a lot of pebbles and gravel from flowing water. Look at all this here. That's from flowing water, isn't it? That's how pebbles and gravel like that's formed. Okay, and this is the artist's impression of what Gale Crater would have looked like between 3.5 and 3.8 billion years ago. Isn't that beautiful? I can't see it because I've got our little Microsoft Teams thingy over here. But anyway, hopefully you guys can see that. You'll see a picture down here to the right of Lake Taupo, and it's about sort of less than a third of the size across. Lake Taupo is 46 kilometres across there. So so that's cool. And there's the Mount Sharp coming out off the lake bed, 5.5 kilometres high. I thought that was just a neat picture of what Gale Crater looked like once. So what can we conclude? And once again, my whole talk, this was one of the last few slides of my talk on Mars and where they were at with investigating it for climate. So I summarised with Mars was warm and wet once with a surface liquid water. Yep, water flowed on the surface of Mars in the past. When probably about sort of 4.1 to 3.7 billion years ago. So, you're talking sort of 400 million years of flowing water and lakes and so on the surface. So go and look up and I do have a handout on that. And of course the talk. Mars then went through a period of experiencing mixed regional conditions. It started getting colder, so you started getting, instead of rain, you started getting snow, and started getting lakes and rivers, you started getting ice, and then you started getting glaciers. And it didn't happen all at once. It was sort of very mixed in a regional sort of fashion. But the last 2.8 billion years, Mars has been cold and dry. But obviously it was once wet and warm enough for liquid water to go on that. So that's sort of with Mars there. So any questions related to that there, Steve?
I just got one question so far from Anne, who's interested to know why the Lowlands are younger than the Highlands.
Oh, why? Good question. How do we know? I know that's not your question, but I'm getting to that. Is that you always date a surface by doing crater counts? Good question. Yeah, you always date a data surface by crater counts. The higher the crater count, the older a surface is. And you might say, well, how do they pin down exact dates? They did that through the Apollo moon landings, whereby they sort of calibrated, if you will. They got patches of different areas of crater rates, and they did radioactive dating of the moon rocks, and then they worked out the correlation to calibrate it. Sort of X amount of sort of certain density of craters, and it goes by the size of the craters. The bigger the craters, and the more of them, the more dense it is, the more likely that surface is going to be older. Newer surface gets wiped over by lava and stuff, and that's one of the reasons we'll come to. Gets volcanic activity, tectonic plate activity, if you're talking about Earth. Of course, that wipes out a lot of the craters, and you get a smooth surface. So you do get a few craters there from asteroids and so on, still slamming into planets to this date. But of course, the big ones have all been used up early on in the sort of more active stage of the solar system. As time's gone on, as the billions of years gone on, there's getting fewer and fewer collisions of asteroids with planets, and they're getting smaller and smaller. So to the extreme where you get very few craters, and what craters they are, they're a lot smaller than these bigger ones over here. So that's how they date surfaces according to craters. Now, your question was why? Well, there's two things going on here. First of all, yes, look, you've got a lot of volcanic activity, and a lot of lava flows would have done that. Lava is from volcanic activity, is probably what a massive cause of giving you flat, smooth, younger surfaces. But another thing that's unique to Mars, he is probably wondering why the dichotomy, the crustal dichotomy. How come you've got the southern highlands, and then you've got this sort of bias towards sort of flat, younger surface of lowlands for the northern latitudes? Don't know. It's speculated probably a collision early on in the formation of Mars, when the solar system was still very busy and planets were forming and protoplanets. Probably two large bodies colliding, or a large body colliding with Mars, is the most likely explanation for that dichotomy with the crustal highlands and the northern lowlands. And as for the smoothness of the surface, lava flows. There's a lot of activity. A lot of researchers came out and see all these craters around here. This region here, initially thought these were a lot of impact craters. But the Mars Reconnaissance Orbiter has found a lot of evidence through doing spectral analysis of the ash within some of those craters, and it's definitely volcanic. And modeling shows that this whole region was once volcanic. They didn't know that a few years ago. This is sort of research that's just been published in recent years, that this was all volcanic activity. So you can, like for example, Olympus Mons, that's this volcano, that's the largest, highest volcano in the solar system. That is about three times the height of Erebus. This is a whole volcanic plateau you got on here, the Tharsis Plateau. A lot of volcanic activity went on there. So I hope that explains it. The dichotomy is probably from a collision early on, and then you've got create the lowlands, and then the lowlands naturally were flooded with lava, giving that smooth, young surface. So I hope that answers the question. So these are topics that we've discussed tonight. Dark matter, special relativity, the sun, the night sky, star clusters, and water on Mars. The PDF handouts, and if you can't find the talks, that's fine. Email me, membership@astronomy.org.nz, and I can send you the relevant links. Here's the introduction to astronomy team. Thank you for your support during the lockdowns of 2021. But we got through. I think we did about half online and half live. And it looks like we'll probably be doing a few more live, but we're working to online rather, and we'll hopefully be working towards, let's hope it's for everyone's sake that we all get through this and come out the other end doing lovely live talks again with a big Santa sack full of treats for all the people who logged in today and got correct answers. I think that's about it, Steve. There's another one of the team. Those are my helpers today, Boston, Stella, and Maya. So a big thank you, guys, for your help throughout the day. That's my team. Okay, Steve, any other questions or anything from there?
No, that's it. No more questions. Thanks very much, Chris. It's informative and entertaining as always.
Thanks, guys, and thanks for tuning in, guys. And so don't be shy. Feel free to email if you need any handouts or links or anything like that. It's all part of the fun, all part of the learning. It's all good. All right, so I'll say good night.